Welcome to the deep dive. Today we're getting into something pretty fundamental, preonics.
Right, from quantum geometry dynamics, QGD.
Exactly. And for our listeners, folks familiar with physics, we're looking at how this idea of preons might actually change how we see the cosmos, specifically redshift.
Yes, redshift is where QGD really offers a different perspective. You see, unlike relativity with its smooth space-time,
The continuum.
QGD says space is fundamentally discrete,
Mm,
granular.
okay.
So our mission today really is to unpack how that core idea, discrete space, leads to, well, some pretty unique views on redshift and maybe even the universe's evolution.
All right, let's dive in. So granular space, what does that actually look like in QGD at the, the absolute base level?
Well, the foundational axiom is space discreteness. So imagine space isn't this smooth sheet. Instead, it's made of indivisible units.
See it?
We call them preons. Think of them almost like, well, pixels, maybe. But building the fabric of space itself.
Okay, pixels. So if space is like a 3D pixel grid at that tiny scale, what happens to our normal geometry? Euclidean space, Pythagoras.
Ah, right. Well, according to QGD, and there's this theorem on the emergence of Euclidean space.
Okay.
Our familiar smooth space, the one where Pythagoras works perfectly, that's actually an emergent thing. It only really holds up at much, much larger scales.
Emergent. So it's like an approximation that works well for us, but isn't the fundamental truth.
Precisely. Down at the level of individual preons, the rules are different. Euclidean geometry, well, it doesn't necessarily apply directly.
So the shortest distance between two of these preon pixels might not be a straight line as we usually think of it.
Exactly that.
Yeah.
It's like trying to draw a perfectly straight line across individual atoms. The concept gets a bit fuzzy at that scale, doesn't it?
It does. And I guess that means our maths has to change too. We can't just use our standard continuous equations down there.
That's the implication. QGD argues that the mathematical descriptions themselves need to be quantum geometrical, inherently discrete, to match that underlying reality.
Which is a big jump from relativity, right, which relies on that continuum.
A huge jump. And it's interesting, even Einstein apparently had some unease about assuming a perfect continuum at all scales.
Okay, so we have this discrete space. What about time? And the speed of light? They're so central to redshift and cosmology. How does QGD handle those?
Time in QGD is, well, it's treated differently. It's not seen as fundamental or physical in itself.
Fundamental.
More like a relational concept. It emerges from the sequence of changes, interactions happening within that discrete space. Think of clocks measuring the rate of physical processes.
Okay, so time flows because things happen in this discrete grid.
In a manner of speaking, yes. And the speed of light's constancy, which is obviously a pillar of relativity,
Uh-huh.
that actually arises quite naturally in QGD. It comes from the discrete space structure and the intrinsic velocity of the other kind of preons plus.
Preons plus. So those are the matter particles.
They're the fundamental units of matter, yes.
Yeah.
Building blocks moving within the preon spatial structure. And they have this built-in speed.
An intrinsic velocity relative to what?
Relative to the discrete space itself.
Yeah.
So the speed of light, which is essentially these preons plus moving, its intrinsic speed relative to space is constant.
Oh, okay.
Now, this leads to a constant metric speed of light. That's the two-way measurement we always do, like bouncing a laser off a mirror. That comes out constant.
By my sense of butt.
But, theoretically, a one-way measurement of light speed could actually vary. It might depend on your own motion relative to that underlying discrete space framework.
Ah, so that's a potential test, isn't it? If we can measure the one-way speed accurately enough.
It's a key potential test, yes. A way to possibly distinguish QGD. But let's bring this back to redshift, which is our main focus. We know Doppler shift.
Objects moving away, light gets stretched, standard stuff.
Right. But QGD introduces another type, intrinsic redshift. And its explanation is quite different.
Intrinsic, meaning the light is already redshifted when it leaves the source. Not because of movement or climbing out of gravity wells later.
Exactly. QGD suggests these intrinsic shifts can happen because of differences in the photon's fundamental momentum right at emission.
Okay, how?
It could be due to the source being in a different gravitational environment, or even subtle variations in the electron energy states within the atom emitting the photon.
Yeah.
The local conditions at the source matter.
So the starting energy of the photon can be affected by its birthplace, essentially.
That's the idea. QGD has an equation that looks a bit complex, equation 3,
Right.
IEP GMP MP plus ACAJA plus AJA, I want to say AJA. It tries to capture these influences on the emitted photon's momentum.
Okay, let's break that down a bit. What are the key parts?
Well, there's a term related to sort of a minimum momentum needed just to propagate in this discrete space. Think of it like overcoming the space's own inertia.
Uh-huh.
Then there are terms for changes in gravity and the electromagnetic interaction right there at the source.
So multiple factors influencing the photon right from the get-go. Can we focus on the gravity part for a second? How does that cause an intrinsic shift?
Let's simplify. Yeah. Look at the part EMGP. This shows gravity's direct effect on the initial momentum. The idea is if a source is in, say, a stronger gravitational field,
Like near a massive star or galaxy.
right, it might emit photons that have an intrinsically smaller initial momentum compared to a source in weaker gravity.
And lower momentum means lower energy, longer wavelength. So
Huh?
it looks redshifted to us.
Exactly. Redshifted right from the start, even before any Doppler effect from motion.
Okay, that's the intrinsic part. Now, how does QGD explain regular gravitational redshift? Because GR has an explanation for that too.
Ah, good point. This is a really crucial difference. General relativity says light loses energy as it climbs out of a gravity well. Work has to be done against gravity.
Makes sense. The photon gets tired climbing out.
Kind of. But QGD says, no, the shift isn't about energy loss during propagation. It's intrinsic, remember. It's the gravitational acceleration at the point of emission that directly affects the photon's initial momentum.
So GR says redshift happens after emission. QGD says it happens during emission because of local gravity.
That's the core difference, yes. A fundamental shift in where and why the redshift occurs.
Okay, wow. So if QGD explains gravitational redshift this way, how does it tackle the big one, the cosmological redshift from distant galaxies, the one we usually attribute to the expansion of the universe?
Well, QGD proposes that the cosmological redshift we see is likely a combination of effects.
A combination.
Yes, part of it is the familiar Doppler effect, galaxies genuinely moving away from us. But another significant part could be this QGD intrinsic redshift, including the gravitational component, originating at those distant sources.
So we see redshift because galaxies are moving and because the light they emitted started off with lower momentum due to their environment.
Potentially, yes. And this is huge, because QGD views space itself as fundamentally static, not expanding.
Whoa, okay. Static space. That throws out the standard expanding universe model, doesn't it?
It certainly offers a very different framework. It suggests we might not need the concept of space itself stretching to explain the observations.
But wait, if space isn't expanding, why are distant galaxies moving away from us? How does QGD explain the Hubble-Lemaitre law? The farther away, the faster they recede.
Right, that needs an explanation. QGD's cosmology starts with the universe as basically a uniform soup of free preons,
Plus.
the matter particles. Yes. Over time, they condense, clump together, form particles, stars, galaxies, the structures we see.
Okay, standard structure formation, roughly.
Roughly. But here's the twist. QGD predicts that gravity, on very large cosmological scales beyond a certain distance threshold, D actually becomes repulsive.
Repulsive gravity, gravity pushing things apart.
On the largest scales, yes. It's counterintuitive locally, but QGD predicts this transition. And it's this large-scale repulsive gravity that pushes galaxy clusters apart.
And the farther apart they are.
The stronger this effect of repulsion, causing an acceleration proportional to distance. So QGD explains the observed recession without needing expanding space.
So the redshift we measure from a distant galaxy is what?
Right.
A mix of its actual velocity due to this repulsion plus the intrinsic redshift from its source conditions.
That's the picture QGD paints, yes. Doppler shift from the recession velocity caused by repulsive gravity combined with intrinsic shifts due to the source's gravitational environment and potentially other factors.
That makes interpreting redshift much more complicated, doesn't it? It's not just a straightforward measure of velocity or distance anymore.
It certainly adds layers of complexity. It implies that simply plugging redshift into the standard cosmological model, assuming only Doppler shift from expansion, might give us, well, inaccurate distances and velocities for very remote objects.
And you mentioned gravity acting instantaneously in QGD. How does that fit in?
Yes, that's another aspect. Because gravity isn't mediated by space-time curvature in the same way as GR, QGD posits it acts instantaneously across the discrete space. This means we also need to be careful about the gravitational environment of our reference source, here near Earth, when interpreting light from billions of light years away. Its influence is felt immediately.
Okay, this is definitely challenging some core ideas. For a theory like this to stick, it needs predictions we can test. We talked about the one-way speed of light. Any others?
Absolutely. Testability is key. The one-way light-speed anisotropy is probably the most direct potential test to differentiate from relativity's postulate of constant one-way speed.
Right.
But also, because gravity is instantaneous in QGD, there's the theoretical possibility, maybe far off, of detecting subtle variations in gravitational interactions with very distant objects almost in real time.
Measuring gravity's pull from across the universe instantaneously.
If the effects were measurable, yes. It would allow determining their position and maybe velocity in a way completely different from using light travel time. That would be another unique validation avenue for QGD.
This has been quite the journey into QGD, a really different way to construct reality from the ground up. Let's try and summarize the key points for everyone listening.
Okay. We've seen QGD starts with this fundamental idea of discrete space, built from preons. Time is relational, emerging from changes within that space.
And this leads to different mechanisms for redshift. Not just Doppler, but intrinsic shifts originating at the source, influenced by factors like local gravity.
Right, and QGD's gravitational redshift happens at emission, unlike GR's explanation of energy loss during travel.
Which then feeds into cosmology. QGD suggests the observed cosmological redshift is a mix of Doppler, from motion caused by large-scale repulsive gravity not expanding space, and these intrinsic source effects.
Exactly. Space itself is static, but structures move apart due to this repulsive phase of gravity beyond a certain scale.
And the big implication here is that if QGD is right, our interpretation of redshift as purely indicating recession velocity due to expansion might need a serious rethink.
It could lead to revised estimates of cosmic distances, maybe affect our understanding of the universe's age and evolution.
Definitely. So the final thought to leave with our listeners.
Well, consider this. If a good chunk of the redshift we measure from the furthest corners of the universe isn't due to expansion, but is intrinsic, tied to the conditions where that light began its journey,
Yeah.
how fundamentally would that change our models of cosmic history, our picture of the Big Bang, of large-scale structure formation? It really opens up some profound questions.
It certainly does. A lot to think about. Thanks for exploring quantum geometry dynamics with us today on this deep dive.